with my collaborator who's in chemical engineering at my university, Patrick Underhill, and our joint student, where we are developing a means of analyzing suspensions of swimming microorganisms with particular attention to stochastic fluctuations. And I may or may not have time to get to the second point, which is work related on the same general problem of trying to characterize what's going on with suspensions of swimming microorganisms. This is kind of more of a toy model that I was playing around with Oleg Zamoransky some time ago, and I may hurry through that depending how much time I have. So both of these models are going to involve stochastic partial differential equations. I'm not going to deal with them in any kind of full rigor. I'm going to treat them as sort of the appropriate physical equations and work with them in a formal way by some sort of smoothing or discretization, as we'll discuss explicitly. In the sense that the usual thing that people who really are serious about doing analysis of SPDEs care about, I'm going to sort of, the things that make them a pain to deal with mathematically are not terribly relevant for the physical situation, as I'll describe. So we'll sweep that under the rug. So actually, I have to make a comment since I'm sort of maybe having two audiences, right? So on the one hand, there's the audience that's here at the Newton Institute, which is who I'm directing the talk to, which is just sort of introducing ideas of what we're doing. The thing I have to comment on is that the Division of Applied Mathematics and Theoretical Physics here is sort of one of the key centers for people who are at the cutting edge of working on the general subject of swimming microorganisms. So we saw Ray Goldstein talking first week. There's Mike Cates, who came last week to our talk, and Tim Headley, and there may be group members who are listening to this. And there's the thing I need to comment on is that the approach that we're taking is kind of coming at this from the sort of applied math and engineering standpoint. And there is this vast field called active matter in theoretical physics, which is covering the same kinds of systems. And the equations and the approaches, they should kind of all fit together, right? But I haven't entirely figured out how what we've been doing, building off of kind of the applied math standpoint, has really integrated in well with the physics literature. So just for those, if there's people who are listening from the physics community, just to give that disclaimer that we're still working on the physicsy aspects of what we're doing here. Okay, some more on that later. So just at the to give you a rough sense of what it is that we're going to be discussing. So we want to talk about what happens when you have not macroorganisms that swim, but microorganisms. So things like bacteria and alga cells and so forth. And there's a key distinction in the physics of these guys from sort of dolphins and people and things like that, which is that the Reynolds number is low, so you sort of don't ever worry. Well, most people don't worry about the effects of inertia, and you are going to see significant effects of stochasticity. Now you could have stochasticity at the large scale from turbulence, but at the small scale you're getting it from a number of sources. Brownian motion kicks in at sort of a codominant level once you get to scales of microns and below. Now most of these objects are a little bit larger than that, so it's not the thermal fluctuations themselves that are necessarily dominant, but there's other things that are kind of noisy about their motion. So E. coli, for example, has this run and tumble dynamics. That's where the noise is sort of coming from the noisiness in the way that the regulatory networks are behaving inside the bacteria, or how the motors are operating. And so there's noise coming from various sources. So for the purpose, so if you want to, there's been, for decades-long study of single objects, single organisms swimming, whether at large scales or small scales. That goes way back. So what's been sort of more recent activity has been looking at what happens when you have a large number of these microorganisms swimming together, or even macroorganisms. You've probably seen swarming and flocking talks about these starlings and so forth. And this is all kind of within the same realm of sort of kind of the individual, the collective behavior understanding. And from the physics standpoint, there's a lot of people are coming into this from the liquid crystals and polymer physics community, because they have all, the statistical mechanics for lots of rods or lots of liquid crystals, and how do they order, disorder, and so forth. And the novelty here is that the objects themselves have like more energy sources attached to them, so that changes the physics, and that's been of a lot of interest in that community. So the point is since we want to focus on the not so much the details of what happens when you have one swimmer or two swimmers encountering each other, we're going to take sort of the typical thing in applied mathematics, where when you want to sort of study collective effects, you simplify the description of any given agent and just have sort of a rule for what that agent does, how they interact with each other, and try to coarse grain from there. So by no means an uncontroversial, but certainly a widely used simplification for the description of swimming microorganisms is, rather than sort of keep track of the details of what they're doing to swim, is that you say the most important thing about their swimming behavior that matters is, well, actually two things, right? One is how fast they swim, right? And the second is what kind of a disturbance on the fluid do they create in order to swim on average. So not like from moment to moment as they're doing the breaststroke or whatever it is that they're whipping their flagella around, but just if you average over a cycle of the swimming behavior, what is sort of the leading order disturbance to the fluid? And there's well-known theorems that come from Newton's third law that say if you have an object that's not coupled to an external field, it cannot generate a force or a torque on its own, right? All it can do is sort of redistribute force within itself, so that it's applying force in one direction in one place and an opposite force in another place to sort of keep a zero net force and zero net torque. And so what winds up being the key quantity is the force dipole, which is just talking about the magnitudes of the forces times their displacement with an appropriate sign. And so the two kind of categorizations, if you want to divide swimming microorganisms into two qualitatively different classes, have to do with the sign of this average force dipole. Right? And so most bacteria fall in this category, where what happens is that the way that they move is that they are whipping some sort of flagella that is essentially pushing the fluid away behind them. By Newton's third law, there has to be an equal and opposite reaction to that backward force, and that's what pushes them forward, so that by pushing backward on the fluid, that propels them forward, and they push forward on the fluid. The fluid is incompressible, so if you're pushing it out in these directions, it has to come in from the side. So that's what the flow field that arises from swimming bacteria looks like to leading order. And in a contrary sense, if you look at algal cells, such as the Chlamydomonas cells that Ray Goldstein's lab has been doing a lot of great work on, that we saw described in the first workshop, it's the opposite. It sort of does like this breaststroke with these little cilia, whatever, I forget what they're called, in front of them, and they're flagella, right? So these things, what they do is they actually pull the fluid in front of them back, right? So it's almost like they're trying to crawl. So they're actually, there's a backwards force in front of them that pulls them forward by Newton's law, equal and opposite reaction. So you see here the difference is that the fluid is being pulled in along the axis of swimming, and then by incompressibility pushed out in the transverse directions. So that's the basic difference of the sign, and then the magnitude of delta is just going to sort of scale with the amplitude of how strong the flow is that's generated by these things on average due to their cyclic motion. Now, this picture, by the way, like I said, this is certainly a widely used picture, and there are studies, for example, Ray Goldstein has studied this Chlamydomonas in detail using these high-resolution video images, and they make statements along the lines that really you need to keep a few more multipoles in the expansion of this guy, and then you get a very accurate approximation. Okay, so all these types of things I'm not saying aren't important, but we're just trying to get our bearings by developing the stochastic analysis for the simplest version of everything, and then we'll worry about the complexities later. All right, so here is the basic phenomenology that was observed experimentally probably about 10, 15 years ago. I'm going to show you just a cleaner movie by David Santian and Mike Shelley, whose work inspired my interest in this subject. And the basic thing that you're supposed to observe from the movies I'm about to show you is that when you have the polars, right, which have the force dipole of one side, then when you have a whole bunch of them together, then thing just kind of looks like a mess. But the pushers, on the other hand, generate patterns. Right? So the sign of this delta will determine whether or not you see some interesting patterning or not. And so these simulations by Mike and David are, these are idealized rods that have force dipoles imposed on them. They're not actual bacteria and so forth. But to some extent, that way they're clean and you can see things quite clearly. So let's see if I can. All right, so what's going to happen is, what's going to be shown first is pushers at 3 different volume fractions. And the more dense they get, the more you'll see the effect. There is no steric effects in these, well, actually I shouldn't say that. In my model, there aren't steric effects. I forget whether they have them in these simulations. So the first is going to show pushers, which will show patterning, and then the last video will be polars, which will look more disorganized. And so those are, just imagine those are idealized force dipoles are moving around. So it's very low volume fraction, and pattern may not be necessarily so evident. So now it's at a higher density. And then you're supposed to sort of see that there seems to be some kind of correlations, at least between the orientations. And here's at higher density, you see things kind of, some structures with some sort of length scale that are kind of being pushed around by the flow that they're just generating on each other. So these are polars at the same high volume density, and I'm not sure how clear it is to the eye or not, but here you see sort of not as compelling a sort of patterned motion as you might have had for the pushing swimmers.
So, excuse me.
Yes.
The coupling is only by the flow?
Yes. And so in my model, yes, in those simulations, they may have a repulsion when they get very close to each other. I forgot about that. All right, so let me finally show you the equations. Now, so the equations are a little bit intimidating. You don't need to remember all this really. I'm going to just tell you kind of like what is the structure that you want to keep track of, right? Okay, so this is essentially we're going to take sort of a kinetic theory standpoint of this. So just like if you had a box of gas, you'd have position and momenta, right? So it's sort of like that, except it's active. And so we still have positions for each of the swimmers. So xi is the position of the ith swimmer. And then we sort of have momentum, but the way that you think about these swimmers is you don't worry about, in the model I'm talking about, you don't worry about that their speed might change, right? You're just like, they're always cranking away their ATP and they're moving at some average speed. The thing I don't know is in what direction they're going, right? So I always treat their swimming speed as fixed, and their momentum type variable is actually just an orientation, a unit vector that says what direction is the ith guy pointing in. Okay, so then what happens is that there's going to be sort of the motion of just the swimmers due to their own effects, and then there's the interaction. So the first terms in each equation are just are the non-interacting terms. So swimmer I will move at its natural speed v along the direction it's pointing, right, on average. And then there'll be some translational diffusion, some noise coming from either motor noise or Brownian motion. And if you're doing E. coli, right, the effective translational diffusion you get by run and tumble, you could put that in a coarse-grained D here. Meanwhile, the orientation, you also have thermal and other noise on the direction. Right? So the direction, you just have one swimmer swimming by itself, the fact that's coupled to a fluid, and it's got motor noise that's going to cause itself to reorient at some rotational diffusion rate. And so this P here is just a projection so that the thing always stays a unit vector. Okay, so the last terms are the hydrodynamic coupling terms. So in this version of the model, That's the only interactions. You don't worry about whether things collide or not. That's a big, issue in practice because collisional effects definitely have a huge role in how these things behave. Mike Cates has done, for example, a lot of work on this. But for now, we're going to neglect those sort of collisional near-field effects and treat everything as sort of using a far-field hydrodynamics approximation. Okay. So this is sort of suitable if the suspensions, this is formally suitable if the suspensions are not too dense, so that you don't have a lot of close collisions happening. All right. So then, so what's happening here is that the way that the hydrodynamics behave is that you essentially have, so you have these K functions, and these K functions are derived from the Green's function for the Stokes equation. Right? So there's a Stokes equation, which is a Navier-Stokes equation with the nonlinear term, the time derivative dropped out. You just have a linear relationship between forces applied and flow. And the nature of this current, so what happens then is what is being applied is you have a force dipole, right, at every place where there's a swimmer. So what's going on here is that the ith swimmer is going to feel a flow induced by the jth swimmer. So the jth swimmer has some direction nj that's going to tell you sort of what direction his dipole is oriented. Then the way that you process that is you turn it into this tensor, right? And then you multiply by this hydrodynamic interaction. And this is just the gradient of the Stokes-Oseen tensor, because it is telling you how a force dipole directed in this direction at location xj is going to create a flow at position xi. And similarly, on this term over here, there is also a torque that's generated by the jth swimmer on the ith swimmer. So depending on how the jth swimmer is oriented and therefore creating a force dipole, there's another hydrodynamic interaction tensor that's related to this one that is telling you how to carry over that force dipole and creates a torque that will tend to turn the ith swimmer due to the gradient in the velocity at its position. I shouldn't have said torque, I should have said that it creates a gradient in the flow which will tend to rotate the ith swimmer. And then delta is the strength of those force dipoles that tell you the strength of the interaction. Now, roughly speaking, I'm not going to write down the detailed formulas because these things they're kind of a little bit ugly to look at, and I don't really need it for the purposes of this talk. So these things decay like a power law at large distance, just like you're used to with Green's functions, right, where d is the number of dimensions. And you, in practice, as x gets small, you'll regularize these things by saying, well, okay, the force dipole, I will use the far field expansion when I'm, large compared to the size of the swimmer, and then if I'm looking at things that are at a smaller scale, I just smooth it out somehow. Right? Of course, you should be using lubrication theory or more fancy near field effects, but we're not going to pay attention to that for now. Then finally, so sorry, as I said, it's a writing. This probably doesn't need much discussion here. So here, these are just white noises that are driving the noise on each swimmer. So those are the basic equations, and this is sort of the physics that's going into what will become some sort of applied mathematics in the upcoming slides. Any questions on what these equations mean or why they are the way they are? All right, so the question then is, what one wants to do is to be able to take some model like this and to come up with theories that will explain, among other things, why pushers tend to form patterns and pullers don't, and more generally to describe properties of the flows and the statistical mechanics of the swimming microorganisms as a function of their various parameters, right? The density, the force dipole strength, and so forth. So there is this, as I alluded to before, there's this vast physics literature, and if you're interested in this, it's reviewed in this paper by Marchetti relatively recently, that essentially directly writes down hydrodynamic equations with terms that are put in to take into account the effects of the active matter. And I have to say that this kind of theory is a little bit hard for me. I'd like to think I know some physics, but this is a little bit hard for me sometimes to understand because the arguments it's coming from a field where there is apparently some heuristics about what the structures of equations look like based on symmetries and things like this. And so just things get written down without necessarily a derivation from microscopic principles. And then, those of us a little bit on the outside are like, wait, where did that come from and why? So I'm going to take a complementary point of view, which I'm in the process of trying to relate to this, but haven't succeeded yet. And that is to proceed from what Mike Shelley and Dave Santian did, which is to work just at the level of kinetic theories, to write down a mean field kinetic theory based on the equations that we've written down before. This you can also think of as a nonlinear Fokker-Planck equation. So that's what I'm going to talk about. Just in passing, I've been working with Patrick also on some sort of a scattering theory as a complement to the mean field theory, where instead of having sort of these things all interact, the swimmers interacting smoothly through far fields, it's the opposite limit where they only interact when they get really close and then something happens to realign themselves. So that's something we're still hashing out, so I'll just mention that we're doing that. All right, so this is what a mean field kinetic theory would look like. So this is just applying standard mean field ideas, and this is what was done by Mike Shelley and David Santian back in 2008 or so. And so what do you see here, right? Well, there's some parts that look sort of harmless, right? So if I forget about the interactions, then this is just a Fokker-Planck equation for the flow and the diffusion, right, for a single swimmer. But what's happening is that, instead of trying to write down a Fokker-Planck equation in 6n dimensions for, the n swimmers and 6 degrees of freedom for each, you're just trying to write down for like, a given swimmer at position x and a given orientation n. And so the way you do that is just make the mean field approximation, which is to say one of two things: either that all the other swimmers I'm going to treat as independently distributed with the same statistics I do, or that all the other swimmers are there's so many of them and they're all kind of infinitesimally small, so that I can treat the sum of my interactions with all of them as just sort of an integral over the density. It's just kind of a smooth density field, not worrying about where exactly they are. So if you do that, what you get is you get a nonlinearity, and that's what's called a nonlinear Fokker-Planck equation. Of course, a mathematician says the Fokker-Planck equation shouldn't be nonlinear. Right, so a mathematician would call this like a McKean-Vlasov equation, right, where you take this approximation, where you're coupling through a large number of other objects, and then you wind up taking a form of mean field limit that you just kind of get that coupling those other terms gives you this quadratic nonlinearity in psi, and this is just the operators that sort of go in to give you that nonlinearity. All right, so I have not done I talked to Tom Hertz at some point about how to try to make this rigorous. Is this a rigorous mean field theory or not? And he told me of some review paper to read that was really, really hard, and I didn't invest the time to look into it. So I don't know if this is rigorous or not, but this is what was done.
Here again next week.
Sorry? Yeah, then I can ask him again and not do it again. This thing, I don't know, I have it in my office. It was by him, right? Okay. All right. So, but the point is that what Mike and David did is they did linear stability analysis on this, and they found that there was always that for polars, the boring stable state, where you just have everything distributed uniformly in space and orientation, is stable, but there's a band of instability if you're a pusher, right? So this kind of would explain why you might have pattern formation in sort of the standard pattern formation way, that the boring state is linear unstable, and so now you excite some sort of mode that can grow until it saturates non-linearly. Right? I should have said too that these type of results are also worked out in parallel in this sort of active matter physics literature, I believe somewhat earlier by Ramaswamy. Okay, so this is great, right? So that certainly gives you some insight, and they simulated the nonlinear mean field equation, got some suggestive patterns and so forth. But there are some sort of limitations to these deterministic mean field theories. One is that when it is stable, right, then the statistically stationary state, right, is all, so if I have polars, so they're linearly stable, so then the only thing you're saying about them is, okay, so they like to just be uniformly distributed. But even if you looked at the movie, something was happening, there was some sort of flow going on, but you can't sort of describe the properties of that flow by just looking at a deterministic theory. And so what's really happening is that that sort of completely boring state is only really true in the limit that you had like an infinite number of infinitesimally small microswimmers that were all sort of smoothly distributed. The fact that you have a finite number of microswimmers, and of course this far field theory requires there to be some sort of finite size effects, means that you're going to get fluctuations about this law of large numbers limit essentially. And it's those fluctuations that are going to, like the fact that this guy is not exactly symmetrically, opposed to this guy, that's going to create imbalances, that's going to generate the flow that'll depend on the number of microswimmers, right? So the finite number of swimming microorganisms is going to have an impact on the properties of the fluid in which they're embedded. And so we're going to take the point of view of just trying to extend this kinetic mean field theory approach with a sort of mesoscopic theory, where we think of the deterministic continuum mean field theory or any sort of continuum field theory as a law of large numbers limit, right? You just have all these microscopic randomness, but there's so many of them in any control volume that they just all the randomness averages out and you get a deterministic equation, right? But if you just go a little bit lower in scale, you're like, well, in each control volume there's a large number, but I don't want to say that the random effects completely cancel out. I want to take them to leading order. Then you have sort of like a central limit theorem type result that tells you that there is a physically correct way to add Gaussian noise to your deterministic equations to describe those so-called mesoscopic fluctuations. So it turns out, despite our initial ignorance on this, that it's a rather easy thing to do. Now, normally, the way that you would do this, like when I teach graduate classes, is that if you have a deterministic system and you want to add the noise to it, there's a fluctuation dissipation relation that says if you tell me the damping mechanism, and if it's a system that has a thermal equilibrium state, then that just tells me exactly what the noise has to be, and you don't even have to think, right? So there isn't really that doesn't directly apply here, right? Because we don't, for example, the concentration field doesn't really have dissipation, it just has diffusion, and you don't really have thermal equilibrium with this active driving. Nonetheless, there is another theory that is also sort of relatively easy to implement once you realize it, that was developed by Dean, and what he did was to show for just stochastic advection diffusion. You just have particles moving around in a flow with some diffusion, and you want to think about, I don't want to just look at the smooth concentration profile, I want to keep track of finite number fluctuations, right? So he worked out that if you, and he did it in some sort of fancy abstract physicsy way, but the way you can do it more in a pedestrian way, which is kind of how I understood what he was doing, is to just think about that if you have your control volumes and you look at the fluxes through any boundary of two control volumes, if you have a finite number of particles on either side, you can characterize sort of the strength of the fluctuations that will happen, right? I mean, of course, you have fixed law to leading order that tells you on average how many particles can go from left to right, but also by knowing how many particles in each compartment, you can generate the fluctuations for that. And the fact that the only process in our equation that has anything to do with randomness is diffusion, right? The most complicated part of our equations is this advection and the flow caused by other swimmers on my swimmer. That's all deterministic, right? So that doesn't generate noise. It's just the diffusion that generates noise. Okay, so actually Mike Cates had sort of realized this a long time ago. I had written down the equation I'm going to show you on the next slide. So we take the same starting point, but we're going to sort of do different things with this equation than I've seen him do in his work. Now, this is sort of my bugaboo, are these papers by Leon Lubensky from some time ago. Instead of starting from the kinetic equation, like I'm showing you before, so like a Boltzmann type equation, adding noise to it, right? They start from hydrodynamic equations, which is how condensed matter people tend to do these types of things. So that's like, let me write down an equation for the concentration, for the velocity, for the orientation tensor, and then I'm going to write down noise terms directly on those equations. That's lower dimensional because it's sort of like keeping, it's like a, the hydrodynamic equations aren't keeping a probability distribution of orientation. They're projecting onto moments, the first and 0th and second moment of your orientation, essentially. So you get simpler equations, you add noise to those. I can't understand how they add the noise to the equations. It's in some standard way that I don't understand. And the results they get from their analysis are different than the results we get from our analysis, and I don't know why yet. Okay, so this is going to be our equation. So what we've done is we've taken the deterministic nonlinear mean field theory, which is up here, and we just added what Dean tells us is the right noise terms, right? And so it turns out, not surprisingly, so it's sort of just like fluctuation dissipation. You've got square root of 2 times some transport coefficient, and so it turns out to be the appropriate diffusion, right? The thing that's a little bit interesting is that the noise is proportional to the square root of the concentration. That sort of makes sense. You think about the central limit theorem that some of the noise should scale with the square root of the number, and if this thing just is proportional to the number of particles, right? And then it multiplies formal Gaussian processes, which, if I'm going to say in mathematically pompous language, are cylindrical Brownian motions, but I'm going to think about them in a more pedestrian way. So I'm not going to write down Q and all that type of thing. Right? Okay, so just for the purposes of how we want to work with these are Gaussian random processes. They're mean zero, and for a physicist of the type that I understand, this is what the correlation function looks like. Right? This is not quite space-time white noise. Right? You've got delta functions on everything, but it's a little bit smoother in time in the sense that if I sort of smooth out space and time, I would have delta t prime here. Oh, sorry, I said it completely backwards. Yes.
Can I ask something? So, but where do you see in these equations, where do you see the finite, the effect of things being finite? Because you would expect that, somehow if you had if you're taking the limit of something going to infinity, this kind of noise term should cancel. So how can I see?
So what would happen is that
easier scaling parameter, right? So you've got the linear in D in the drift, and you've got the square root of D in the noise. That's exactly the kind of noise you get in all of these chemical Boltzmann equations.
Yeah. So this is just the. So I think it's more the fact that these guys are scaling a square root of psi. So psi itself. So I'm going to think about psi not as a probability density, but as a phase space density. Right, that's sort of the way that sort of the theories were actually intended to be developed. I think it's easier to think about them in those ways. So if I think about this as the number density of objects that are located at position x at orientation n, then if I put more things there, then psi will become dominant relative to the square root of psi. Those terms become subdominant. Okay. So definitely, when you pull out the, I'm not going to probably do it for you on the slides, but when you do the non-dimensionalization and pull out the number of swimmers in the system, then these guys become square root of 1 over n as large as the main terms. Okay. All right. So the sorry, I said this wrong before. So the way that it's not like space-time white noise is it's actually rougher in space because you're not integrating over space. You're integrating over time, so that's where it's kind of a little bit smoother. And so in fact, it's nastier than what you're used to from ordinary stochastic differential equations. So if I just sort of naively discretize things, then I'm going to have sort of these kind of horribly blowing up correlations of what's happening in one spatial voxel and another one. And in fact, so if you try to make sense out of this, and this is probably well known to many of you, is that not only you have a hard time making sense of what the solution is to such an equation, whether it exists and so forth, even the noise itself, right? It's not going to converge to anything. It's sort of really sort of not worse than, it's worse than sort of the normal Brownian motion in ordinary time. And of course, this gives you some numerical worries. Now, so I don't know whether this is well known. Are people kind of, yeah, we know that physics equations tend to have these really bad space-time white noise things, but they're actually right? Anyone want discussion on that, or should we just bypass this?
I want a discussion.
Sorry?
I want a discussion.
Okay. All right. So here's the deal. So the point is, I mean, the normal thing you would say is that, if I can't develop a well-posedness theory, if I can't even sort of, if I just even look at these terms and imagine just, refining my mesh, and my solution is not converging as I refine my mesh, right? Then you're like, I mean, what are you even talking about, right? Okay. The point is that what's happening is that it's a physically correct problem. And the fact that what's happening is it is true that if I simulate a fixed system, fixed parameters on some mesh, it's going to have a certain level of noise. And if I refine the mesh, the noise will get worse. If I refine the mesh more, it'll get even worse. Right? The mean square velocities and so forth will get bigger and bigger and bigger the smaller the box that you look at. Right? And so the issue is that what's happening is when you're looking at these particle densities in a numerical way, right, you're always going to be sort of representing them in terms of some finite volume V, right? And the fluctuations, right, of volume V will be on the order of the number of particles in a volume of size V will scale as square root of V, and when you divide by V to get a density, the density will scale like 1 over the square root of V. So just even looking at the same system at a different levels of resolution, the density will look rougher and rougher and rougher in proportion to 1 over the square root of the volume as I refine the mesh. But the point is that to some extent you don't really care about that, because if you're working with a continuum theory, you don't ever really mean to take the limit as delta x goes to 0, right? It's like delta x is small compared to anything I care about, but of course it's big compared to atomic level things that in quantum mechanics, quantum effects, and so forth. So there's always a lower cutoff scale that delta x is small compared to things you care about, but it's you never really want to take that it goes to 0. And so what happens is in practice is that if you were to look at an actual physical system experimentally at small and smaller scales, the fluctuations would scale in the same way as this model would until you got to the point at which the continuum theory was just garbage, which would be on the scale of about 10 nanometers, and then just, who cares, your theory's wrong, right? So who cares that the noise is wrong, right? The deterministic part's wrong as well. The good news, though, is that if you take formally, again, I haven't proved anything about this, but if you formally take solutions of the stochastic partial differential equations and project them onto smooth large-scale modes, like a fixed number of Fourier modes, and you take the mesh size to 0, that will converge. Right? So as long as you ask questions that involve averages or filters of your field variables on fixed scales, those will converge as you tend to send the mesh size to 0. It's only point values, like what's a mean square value of this, what's happening on a voxel, and as I shrink the voxel, then I keep asking the question about those shrinking voxels that I run into problems. And again, if you want to get more serious about this, then Martin Heyer is over at Warwick. So we okay on this, or further? All right. So the point is that I get kind of nervous thinking about trying to do numerical methods where the noise is blowing up as you resolve your mesh. So I had to deal with this before when we did this. And by the way, I should have said, of course, Sam's worked on issues with the fact you can't resolve box sizes and reaction fusion systems for related reasons, of course. Okay, so I had to sort of encounter this problem of having these space-time white noises to deal with in the stochastic Morse boundary method. And the way that we handled this from a numerical standpoint is to make the numerical approximations themselves physically meaningful. And the main reason for doing that is that if you just sort of arbitrarily discretize the system, like let me just discretize the noise and discretize the deterministic things, then if the noise and dissipation aren't discretized in a sort of a consistent way, you can throw off the equilibrium properties of your system. So for example, if I want to characterize the strength of the patterns that are generated by the swimming microorganisms, then the dissipation, right, is going to damp them down, and it's the noise that's going to generate the amplitude of the patterns. And so if I want to get that right and to converge as the mesh size resolves, I better sort of put in the balance between the dissipation and the noise, which comes about either by fluctuation dissipation relation or this kind of Dean theory for these sort of transport equations. So what we're going to do is, this is almost sort of like doing the backwards thing of what a lot of you do with, you know, going from a master equation, getting a chemical Langevin equation, right? So we're going to do this in reverse. We're going to make numerical approximation. So we get the chemical Langevin equation because we start with the continuum theory, we add its noise in sort of the perfect way to that. And now we're going to sort of back out some master equation that's going to relate to that, right? And I guess this is somewhat related to what Tomislav was talking about as well, as sort of what kinds of systems are consistent with a given chemical Langevin equation. So we just want one that's reasonable. Okay, so what we'll do is we're going to put everything on a spatial lattice, and we're going to just represent the velocity and diffusion by hopping rates, and I'll just keep time continuous here because it won't really matter. So this is probably going to be well known to many of you. I'll just sort of breeze through this. Rather than show how to do it for our equation, all the complexities, we do the same idea as what you do if you had a noisy advection diffusion equation, right? You discretize space in intervals of size delta x. You just have the number of particles in each box, right? And the particles there's a velocity associated to each box depending on the current flow at that box. So of course, this v could depend on time. It doesn't change anything. All right, and then you just write down, okay, so what do the hopping rates have to be to give you the right velocity and diffusion, and there it is. And so here's something that I imagine must be well known to some of you, but it was sort of a little bit of a novelty to me, is that for this to work, the Peclet number has to be less than or equal to 2, otherwise you get a negative rate. So if anyone, I'm sure people know about this, but I don't have a reference yet to it. So if someone can tell me where someone's pointed this out already, I'll appreciate that, right? So in order to avoid this guy being negative, you have to have that your mesh size is small enough that the product of the velocity times the mesh size is small compared to the diffusion. So then what we do is do a sort of a cheap tau leaping approximation, right? So we just update the numbers at each step by sort of counting using these hopping rates, how many things are jumping from j to j plus 1, and keeping track of all the fluxes. And so we could do this at 3 different levels, right? We could make a binomial model out of it. We could make a Poisson model out of it if there is, if the number that are switching is, if the numbers are large, the number of switching is order 1, or what we will actually wind up doing is the Gaussian approximation, which is that if you have a large number of particles switching at every time step, then that would be appropriate. Now the problem with the Gaussian noise, I've talked to some of you about this, the fact it doesn't preserve an integer is not so worrisome, but it can, if you're not careful, ruin the the fact that these densities have to be positive, right? But it's also easy to simulate. So anyway, there we go. So we write down the density, we write down the flux, we just count the number of particles that move over a given time step, and here's the equation that we get. So, so one thing, again, this is, I'm sure, well known to many of you who work with these reaction fusion master equations, is the only consistent way that I could figure out to derive a numerical method that had a sort of this self-consistency between noise and dissipation was to use a central difference operator for the advection and the diffusion, and then the corresponding central difference on the random fluxes, which are Gaussian. Right? So that's annoying because, I mean, if we didn't already have the fact that Peclet number is less than 2, we know the center differencing is unstable if the Peclet number is bigger than 2. So that's yet another reason the cell Peclet number has to be smaller than 2.
So what's the problem with upwinding?
The problem is, well, that's the point, is that my collaborator had existing upwind models for the deterministic theory, which is what you want, because surely the flow is strong compared to the diffusion effects, right? It's definitely a convection-dominated system. But I am unable, so this might be some fun thing for anyone who wants to talk to me about this, I am unable to derive a upwinding scheme, I have not succeeded in deriving an upwinding scheme that is consistent, that comes from a stochastic model that is statistically self-consistent.
Isn't that coming from the way you choose to give the weight R minus and R plus?
So any different choice, right? So I'm constrained up to order whatever it was in delta x to make those choices, and if I have some flexibility in higher order to add different terms, but those will all be subdominant in like third order. So here they will not change the fact that it's center differencing, if I recall correctly. I've talked to some people about this, but not you guys, and you guys probably wouldn't be in a position to know. So anyway, I'd be happy to hear a way to make this upwind. Okay.
Can I ask something?
Yeah.
Where does the Gaussian approximation comes into that? Sorry.
Just here. I mean, the fact is, here, the only thing that Gaussian does is makes these guys Gaussian. So if I had chosen Poisson or binomial, everything would be the same, and this would be binomial or Poisson, with appropriate variance and blah, blah. Yeah, by the way, so one of my colleagues in computation said that Enquist, I believe, was giving some talk that had to do with coupling a continuum model at the boundary to some sort of more, stochastic model. And there was some, it kind of went by in a slide, and you can tell me the details, but there was something too with either there being I forgot whether it was a restriction on signal differencing or the Peclet number being small in order to kind of be able to connect the continuum solver and stochastic solver. And so anyway, obviously, I'm a little bit fragmented in my mental picture of this other than what I've shown you. All right, so in a few more minutes. So that's the numerical method. It's been implemented, and but I'm not going to show you results of it because this thing isn't necessarily positivity preserving, right? And the way that it's being done now is embarrassing, and so it produces numbers and it produces things that look okay, but I sort of don't quite want to talk about it in public yet. Yeah.
I have a question with that. So you said before that delta x cannot go to 0, right?
Yeah.
And so what is how can I measure whatever on this numerical scheme, set the parameters, how can I choose? So of course you have a restriction with this Peclet number, okay? But that's just a practical restriction, right? But usually, you set the parameters because you want a certain approximation. So how do you set the delta x here?
Right. So I mean, so the delta x being too small was simply a statement of saying the equation itself is complete nonsense if delta x is too small.
I understand. But
the numerical method I can make delta x as small as I want.
Yeah, but so in practice, I mean,
In practice, of course, so what you do is you have, you have the v and the d are given you from physics. And you just choose delta x small enough so the Peclet number is smaller than the things don't, right? Yeah, so delta x doesn't have physical meaning, right?
So you just want the scheme to be stable.
Yeah, it's just a numerical parameter. We want it to be small so that the solution is reasonable.
But you were saying that whatever statistics you're interested in will converge as you shrink delta.
Formally, yes. Okay. So the last thing that I will talk about regarding this is some theoretical work that we to complement this, and the reason being is we want to sort of cross-compare our finite difference simulations with some kind of systematic theory, and so far the comparison is pretty good. But again, I don't really like the implementation, so I will just sort of tell you what the theory is. So. Okay, so this is what we're going to do, same thing as Lau-Lubensky do on different equations, which is just to do a linearization about the boring steady state and see what the noise does. And so the point is, of course, if you're unstable, then you have noise plus unstable, and it's fully nonlinear, and you have to do something harder. So we're just going to do this very simple thing, which is to look at what do the noisy fluctuations look like when the boring state is linearly stable, And the point of this would be to get non-trivial results, for example, for polars, which the deterministic theory, all it tells you is everything's kind of nice and boring, but doesn't tell you how strong fluctuations would be from having a finite number of swimmers. And for pushers, also there are, if the rotational diffusion is strong enough, they will also be linearly stable, so we can characterize their fluctuations as well. All right, so the details of this are not going to be terribly interesting to you. I'm just going to sort of talk through this at a high level. The most non-trivial term in the linearized equations, right, that comes from these hydrodynamic interactions are given by this operator. And this is the qualitative features of the operator. So in space, it's strongly singular, right? It's got sort of two antiderivatives and two derivatives. Right? And then with respect to orientation variables, what's happening is it is essentially projecting out the second moment of the orientation variables by integrating against n prime tensor n prime. And then it's re-injecting whatever you get from doing all this back into the second moment because there's two n's on the outside. So gamma is a parameter that characterizes the shape of the swimmer, dynamic viscosity, projection onto incompressible part of function space, and the advection term is very simple, but it actually stops the thing from being very easy because it will couple different orientation modes because of the coefficient of n there. So what happens is, in the end, you know, abstractly, what you get is just some glorified. If you take a Fourier transform in space, then you get a glorified Langevin equation. So you can think about what these guys are. It's for a fixed spatial wave number, but you're keeping track of all, for any given k, you have this vector representing the projection onto all the orientation modes. Right? And this LK operator is going to have some sort of mostly tri-diagonal coupling between them. Plus some extra term coming from that strongly singular operator. You have then you have noise coming from translational diffusion, rotational diffusion, you know. And so this thing you can just sort of do standard linear Langevin analysis to get results for. And now these are formally infinitely dimensional, so we have to truncate these guys at some large mode cutoffs by Galerkin truncation. And another thing we've been able to do theoretically is to get some analytical results in addition to the numerical. So what do I mean by numerical results? I don't mean we're simulating these things. I mean when you write down the matrix equations for the statistics, you get, you know, you have to solve for the eigenvalues of some matrix that you don't know what the eigenvalues are analytically, so that's what you have to do numerically. But we can't get around that if the wave numbers are small enough compared to some of the physical constants. All right, so then you write down superposition of space and orientation modes. The results I'm going to show you are non-dimensionalized. The small parameter in the linearization turns out, when you do all the non-dimensionalization, to be 1 over the average number of swimmers in a reference unit cell. So that's where you sort of get the effects of finite swimmers, that if you were to take the number of swimmers to infinity, then the magnitude of all this would be multiplied by 0. Make it go away, will it? Something else come up. All right, so what I'm going to show you is the following fundamental statistics for various fields. So there's various physical fields that we can define. One thing that we can do is we can characterize the root mean square size, just how strong the field is. And the other fundamental characteristic is the correlation length. It basically tells you how far from any given point does the value of the field at that point influence the value of the field at other points. So it turns out that the concentration field in our model, so if you're just talking about how many swimmers are at a given location, that there is not a significant, for either there's not a significant clustering that happens and things kind of bunch in or bunch out. Those kinds of things definitely do happen if you turn on near field effects like collisions and lubrication theory. And so, for example, there's some work by Mike Cates that looks into that. But that's beyond the scope of the model that we have. Here is something that's a little bit more interesting. If instead of just looking at the number of swimmers at any given location, what if I can look at sort of the orientation field, which is like go over space, I'm just asking, what is the average direction which swimmers in this region are facing? So I look at that, so how you can read these figures. So pushers are on the left, and they go unstable if the rotational diffusion gets off the graph here, right? So then there's linearized theory doesn't really do anything for you. And so not surprising, what you see is that as you approach, as you reduce the rotational diffusion so that you're making the pushers less and less stable, their amplitude of orientation is growing, as does the correlation length. Polars are always stable, but as you reduce the rotational diffusion, the amplitude doesn't change much, but you see that the correlation length increases a little bit. That's not so much to write home about. Here's something that's a little bit more interesting, is if instead what I look at is I say, what is going to be the velocity field, right? So imagine I look at any particular region and I say, okay, based on where the swimmers are now, what is going to be the fluid flow at that particular location? And there's the formula that you get for that. So pushers, not surprisingly, but again, as you push the rotational diffusion down to instability, both the amplitude and the correlation length are going to get large. Interestingly, for polars, as you reduce the rotational diffusion, the amplitude of the velocity and its correlation length go down, right? So this is, it's not going unstable there, but it's just as you're weakening the dissipation effect, the strength of the fluid velocity is actually getting weaker. And the rough reason you can understand that is that the polars, to some extent, have some kind of cancellation effects, right? So that if you let them do their thing, they'll tend to align themselves in such a way that they create flows that are going to cancel each other out. So if you reduce the noise, the kind of cancellation phenomenon is stronger, and you actually reduce the strength of the velocity field. You can look at things in correlation functions in time as well. That's just completely related to the properties of the eigenvalues of this linearized operator. It has some imaginary parts. You see some oscillations for pushers at least. I think that's probably I'll stop there, and people want to hear about toy models, they can talk to me offline. So the upshot is that what we've developed here is we've looked at a rational model for introducing noise to the mean field kinetic theory representing swimming microorganisms, and we've talked a bit about trying to how to work with that computationally, as well as to do some linear stability analysis on it to get some statistics where the deterministic theory is uninformative. So again, I should say that these things have also been done from the hydrodynamic perspective by the physics community with results that aren't always the same we're getting, and we're trying to resolve the differences still. And what we're working on at the moment is computing more subtle properties that require more work than just a sort of linearization, like from this theory, how do we develop or calculate quantities that characterize the mixing properties of the flows generated by these swimming microorganisms and the viscosity, and then try to think about what we can say when we're beyond the linearly stable regime. So we want to take into account the fact that the equations are really nonlinear, then how do we do that? So I'd be happy to take any questions.
The dipole model, and you said the higher order corrections, what is the base model that they're deriving that from?
So what you do is you can, everything starts from Stokes' equation, and okay, so there are.
How do they treat the cells, the swimmers in those?
Yeah, so if you saw Julius's talk last week, what you can imagine doing is putting on the surface of the swimming object these force structures,
So the
stress
swimming
lets, Stokes
object
lets.
is rigid or elastic?
Well, there's certainly elastic, right? The flagella part is certainly elastic. And so there's some procedure by which they put down a distribution of forces along the edge of the swimmer.
They do Stokes with approximation.
Yeah. And then you integrate over that, and in general, the far field, the leading order term would be the dipole, but you could get higher order terms. people like Yeomans, for example, they wrote a paper where they looked at two swimmers and they argued that you can't just sort of average out the motion of a swimmer. You actually want to take into account the time dependence of the shape because that can affect how two swimmers encounter each other. And it's true that one thing that hasn't been worked out, to my knowledge, is these forced dipoles are a coarse graining of a single swimmer. And it's not entirely clear, certainly mathematically, that if I coarse grain a system of swimmers, that's the same as the system of coarse grained swimmers. That's where we're at for now.
And so have they compared these? I assume they've done like simulations with small numbers of explicit, like realized swimmers, with the real geometry. And did those compare pretty well with the swimming models?
Yeah, so this is a lot of what my collaborator does sort of on its own. And I mean, there is, how shall I say this? Yes, because these mean field theories work in some regards, but not others. So there's some quantities that compare well and some where there's a clear deficiency. So it's not a perfect theory by no means. Yeah.
So when you say the discretization doesn't converge to the full to the PD models, SPD models, when delta x goes to 0, is there a theory that explain if you do both discretization in time and space and couple delta t with delta x and together, then you do indeed converge to?
Well, first of all, you have to have a well-posedness theory for the equation, right? And getting well-posed theory for these kinds of equations, to my knowledge, that the way you do that is you read Martin Heirer's book, and there's this very delicate interplay between, as you're saying, how you take how space and time relates to each other, and it's a very delicate process, and I'm not sure it's been developed for equations of this complexity yet.
Because in the end, your model is both discretized in time and space, right?
Yeah, but so I guess my point is, I don't ever really want to think about this as there really is a delta x goes. My point is, how shall I say, if I discretize this at a scale delta x that is much smaller than anything I'm going to measure or ask about it. So if I'm only going to look at, I'm not going to take seriously if it says the correlation length is delta x, right? But if I'm looking for things that have correlation lengths that are kind of, some reasonable fraction of the domain, then if delta x is small compared to that, then in a formal sense, the answer shouldn't depend on delta x. But I don't know if I'm answering your question.
I don't know that.
But you said before, you said at some point that when you would project this SPD on some smooth mode, so then you can show well-posedness.
Formally, right? If I write down the equations for Fourier modes and take the formal limit as delta x goes to 0, those equations, the noise converges to something, Gaussian noise with a finite variance and so forth. Whereas in the SPD itself, just take the formal delta x goes to 0 limit, everything blows up.
But then there's a discretization of this smooth with SPD also, right? And this would converge to the SPD, right? And then
no. So if I simply do like a Fourier transform and a Galerkin truncation, right, of Fourier modes. If I look at a given Fourier mode, right?
Okay.
I'm not doing anything sophisticated.
So can I ask something on that point? So, if that SPD is not the correct model, so why
It is the correct model.
Sorry?
It is the correct model to a physicist.
To a physicist.
And to me.
But in some sense, wouldn't it make sense to have something similar like the reaction diffusion equation there, and then have sort of like boxes of given size?
Yeah, but the problem is, I was thinking about this, which is like, why not approach this the way that most of you are approaching this in terms of chemically reacting systems? But I guess you're starting from equations that really want to be posed or sort of naturally posed in continuous space. Stokes' equation, for example, right? Of course, I could force a discretization on it and say I'm going to just put things in boxes. That's essentially what I did, right? But the sort of the right equations sort of come most naturally if you start from continuum formulation and discretize later. And we can talk about it. There might be a way to do it the other way, but it's sort of an unusual way of thinking about.
But your smallest delta x, in some sense, in that case, is how big the microswimmer is. Yeah, if you go to a voxel that is smaller than the size of the microswimmer.
Well, certainly you could not. I would say delta x should be large compared to the size of a microswimmer.
Yeah, but I'm saying the smallest it can be.
I mean, there's absolutely, yeah, if delta X is small in microswimmers, it's garbage, right?
Yeah, so I mean, this could kind of, so you know that this is kind of the smallest delta X, because if you take it smaller, you're gonna have 0.2 microswimmers or
Right,
something like
right.
that, which doesn't make any sense. Okay.
But it doesn't matter. I mean, formally, it all just works, right? Formally, the SPDE is just a way of thinking about the continuum limit of these discrete
That's
processes.
exactly right.
But, you know, yeah, I mean, I still don't get why you don't just start with the discrete formulation of the problem. You know, when I first learned about the diffusion equation, right, I learned about it starting with little voxels and thinking about what flowed from one box to another. I mean, you can start from that and think about the limit that way. And then I think probably it will all work out nicely, right?
Yeah, but I guess my point is, it's, somehow then you have to sort of formulate this all in terms of boxes.
Right, but that comes out naturally, right? So I was inspired by Sam's tutorial at the opening workshop, so I decided I was going to do reaction diffusion spatially, right? And if you start with the reaction diffusion master equation, if instead of just letting the space go to 0 there, right, because obviously that has problems, right? You first do a chemical Langevin equation, you get a set of coupled SDEs that look almost exactly like these, and they have a really nice, obvious natural limit as an SPDE for the reaction diffusion process.
But aren't those SDEs for chemical species numbers?
Well, they are.
And so what I'm saying is the difference here is that my Langevin equations are for positions themselves.
Right.
So I'm thinking, I mean, this may be a good thing to do. I'm just saying it's, to me, I was thinking about this and it's not clear to me that it's a direct technology transfer from doing it for chemical systems to these guys. Because I think if I understand correctly, the spatial motion in these chemical systems is sort of simple diffusion and maybe some opposed flow.
But you said all of the noise is coming from the diffusive bit anyway, which makes
That's
me think,
true.
Which
So
makes me think it should just work.
You may reformulate this by saying that all xi which are the same position or the same voxel, put a new variable which is the number of gas which was in this voxel.
so I mean,
You should end up back to
I think
chemical.
the discretization I do later, you're simply saying I should do, you would prefer I do that at the beginning.
Yeah, I mean, that's essentially what he's deriving, right?
Yeah,
You
sure.
could take the opposite point of view and say, that's
Yeah.
my model, but you get the same thing out when
Yeah.
you go up.
So I guess to some extent, maybe this is sort of an audience that prefer I do it the other way, but usually I'm not with it.
But it
There's
does
two advantages. So one is that you get the noise with the right form for free without having to worry about it, right? And the other thing is you also get the discretization for free without having to worry about where the discretization comes from. So you get those two things kind of
But
automatically.
you're imposing a sort of artificial discretization from the start.
Is it artificial?
This is what I don't understand is
It comes to the question to what converge a numerical solution. So if you start as he says, then you have at the beginning something that is the exact model, right? And you don't have to question to what it converges. I mean, this troubles me a bit. You know.
I don't quite see, in what you showed, what the problem with doing a different, representation for the effective part, what difficulty that gives you, I guess.
Simply that if, and this is just me playing around and not knowing the literature or whatever, but if I just write down like, okay, I'm gonna make, I don't know if I thought about yet having hopping to not nearest neighbors, but that sort of bothers me a little bit. But if I just have hopping to nearest neighbors, the velocity and diffusion constrain for me the leading order behavior of the hopping rate.
Sorry, what constrains it?
The velocity and diffusion. So if I just say I need to have the right velocity at this point and the right diffusion at this point, it constrains the numerical method to high enough order that the leading order is center difference.
What do you mean by the right velocity and the right diffusion?
So the point is that when if I look at this equation, right, so I have, and really this should depend on time as well.
Yeah.
And when I discretize this, right, I need the mean, I need this to mean something in terms of the hopping rates, right?
Sure, but suppose you had an upwinding, right?
Yeah.
Then for a single molecule, you would get back its diffusing and it's got that
So
velocity.
if I'm not mistaken, the upwinding is always going to give you extra diffusion, right? I thought was the whole point of why.
But not in the continuum limit, right? You'll get back.
Oh yeah. So I'm
Okay, so it's more than that you want to recover the correct continuum behavior. You want
oh yeah.
on
The thing was
discrete level.
That's right, because in some extent, if I'm introducing extra dissipation on the discrete level, then I've broken the balance between the noise and the dissipation.
Okay.
And that's right, you could say, you might argue that that is a, but I think, as I'm thinking too, is like, oh, maybe it's a small effect, but if you're, it's only a small effect if the cell particular number is small. Right.
There are not any other questions. Let's repeat again.